Hello everyone and welcome to this finally released After Effects new GPU setup plugin tutorial. This will work for Premiere as well with some modifications, but for all intents and purposes today it's going to be about After Effects and setting up all the new GPU stuff that they have figured out for us. In the past, you may be familiar with things like OpenGL, which were very popular, but as time goes on, these are becoming more obsolete. And for me, that environment with Vulkan, OpenGL, and all that can be a bit daunting. And Adobe has released a sort of new setup in several versions of After Effects that allows us to basically write one GPU kernel or one bit of GPU code and have it work on Apple Metal devices or Apple Silicon, OpenCL devices, or a lot of Mac and sometimes older Windows devices, as well as CUDA or NVIDIA graphics cards. This tutorial will consist of several steps of important setup, both on Mac and Windows. And we're going to be following this, which I'll be putting in the description, this basically README for how to set everything up. We got to prepare the environment for Windows and Mac, which involves installing Boost on both systems. If you're on Windows, we're going to be installing a CUDA driver to make sure the CUDA toolkit works properly. And then we're just going to set up a couple of variables, and then we need to learn about the example project provided, how to set that up for the first time, which can be tricky. And then we can basically just dive straight into the GPU code and have things run a lot faster. Now, before we hop into it, I do want to say this GPU setup does have some limitations, but it's also incredibly powerful and fast. We're talking about blur operations and other convolutions taking a fraction of the time. And now that After Effects tells us how long things take to render, you can really see the results from going from a CPU process over to a GPU process. So make sure you check out the code down below. This guide will be attached with everything you need to know and follow along. Follow us down there on GitHub as well, Instagram, join the channel and subscribe, and let's jump into it. So we're going to start with Windows, move over to my Mac here, which is recording simultaneously, and hop onto each section that we need to get things running. So number one, you're going to need the SDK guide. This will need to basically just be the freshest version. I believe it's been around for a year and a half, but it's easiest just to use the newest SDK. So I have my After Effects SDK, and I am in the examples folder where we have a thing called AE GPU SDK instructions. These are the instructions for setting things up on both Mac and Windows. These are just the libraries set up essentially. There's a lot more setup that they don't discuss, which is why this tutorial has been approximately 4 to 6 months in the making. In terms of the actual example project we're going to be using, if you go into Effect, we have something called SDK Invert ProcAmp. This is an example project which essentially will do two processes. One of them inverts the image, the other applies some different things like contrast and brightness. And inside of here is going to be the actual project we're modifying in order to get everything up and running. But first, we're going to take a look at what is presented to us in the GPU SDK build instructions. We're excited to introduce you to the new AEGPU SDK in 16.0. It's a bit of an old message. Please see the SDK Invert ProcAmp as an example, and more information can be found in the guide. So we're going to start with Windows real quick. The first thing we're going to need is Boost. Boost is basically a preset library with a bunch of useful functions, and in these sort of technical terms, what Boost is going to be doing, among other things, is basically converting our kernel code, I believe, to different code. I haven't gotten too deep into it, but setting it up is very important. So we're going to go to boost.org, unzip the Boost package and run bootstrap.bat, then run b2 to build Boost. So we'll go to boost.org. We can download the current release, and we'll just download the zip file. And then also while that's downloading, I can go ahead and take a look at the next step. We also need to install the CUDA SDK for NVIDIA, and you must have an NVIDIA GPU, of course, with CUDA enabled for this to work, but pretty much all, even old cards and modern cards have this. We can basically go to this link to download it, and it says, please use the same CUDA version that your AE build is using. AE 18.2 currently uses CUDA 10.1. So I personally have CUDA 10.1 installed already, But what you want to do is basically just go to their link, and probably we don't want to change our tab here. We can say we want Windows. I'm on Windows 10. And let's do a local exe. And this is how we can begin downloading it. But it looks like we're looking at CUDA 12, which may work, but just to be safe, you should probably use the version they recommend. You can see an archive of previous CUDA releases, and we can scroll down to find 10.1, and basically it's best to go with the most updated version. So if you get 10.1 update 2, that's the most up-to-date version. Select your OS, all that stuff, and then you can download the CUDA toolkit in the right version. Now while that's downloading, let's take a look at our boost folder. You can see we have several subfolders in here, and the instructions simply say to unzip it and run bootstrap.bat. Now I do have a previous install of Boost on here, 1.71 to be exact. So what you can do is just copy where I have it located here. Basically all you got to do is move all the folders to somewhere that you predefined. For me, I just put it in my C drive and then the Boost version. And then you can run the bootstrap like it says. And then remember, it also says we need to run the B2 file as well to build it. So first we're going to run the bootstrap bat, and that's going to build Boost. And then you can just double click on the b2.exe file to finish the build process. This is just going to set everything up in the background automatically for you, but also just make sure you remember where you put Boost. In this case, an easy place to put it is directly in your main hard drive, root, and then the Boost folder. And the Boost root folder should have all of these contained within it, like an index.html, the license, and all of that. So that's setting up Boost. Pretty easy on Windows. You just download it, run 2 files, and it does everything automatically. Now for CUDA, we downloaded this, so you're just going to click on the installer for the CUDA installer and basically go through the prompts and have it install on your system. You'll definitely want to make sure you use the right version, because I have had issues in the past with versioning. So if you do have issues just in the beginning stages, try just using a certain Boost version, maybe 1.7, and a specific CUDA version like 10.1 update 2. All right, next we need to set up environment variables to make things easier to basically locate. So on Windows, you can just type in environment to edit the environment variables. And we need to set up a CUDA SDK base path and a Boost base path. These will go under system variables. So you can see here I have created a new Boost path, which has Boost base path as the name, all in caps. And then I have a direct reference to the folder where I installed Boost, as we just said, in my C drive root, Boost version number. That's going to allow us to basically easily reference Boost, which is required for the GPU setup, and not have to hard code the paths. Then we're also going to set up a CUDA SDK base path, which is usually referenced in your program files, NVIDIA GPU Computing Toolkit CUDA, and then all of your versions of CUDA will be located in this folder. So again, all you have to do is go into your environment and then system variables, create a new CUDA SDK base path and a new Boost base path, and reference those exact paths. So that way when we tell Visual Studio where those are located, it's going to easily know. So click on OK to save any changes and OK to close. And because I've used this template so many times, I need to basically bring in a new copy of the SDK invert proc amp. So I'm just going to do that real quick, put it inside of here, and we'll just say tutorials SDK invert proc amp. Okay. Our next step is to actually open this project. So I'm just going to use VS Code 2019 for simplistic purposes here. And then I'll navigate to my SDK proc amp VCX project file, which is going to load up our SDK proc amp setup. We'll click on OK to just get it all loaded here. And here we have our plugin. We do have one more instruction as defined here. Modify the Microsoft compiler path in the CUDA kernel custom build steps. Now, if you're unfamiliar, whenever you right click on files and things, they have properties very often which can be modified of their headers, or sometimes when you have things like kernel files, we can set up the compile options. So this is a bit of a discussion before we do this. The basic setup of how the GPU plugin works. We have our normal plugin setup with the CPP file with all of our useful fun code where we set up the about, we set up the global setup, we set up the parameters and all of that good stuff. We also, of course, have our resource files where we define the match name and all of that. And we have the header files, which contain any of our required libraries. In this case, it's a little more complicated, and also our enumerations for our param setup properties. But we also, as you can see, have this .cu and .cl file. The .cl file is basically empty and just refers to the CU file. Well, CL just references OpenCL, which is a GPU way of processing things. And the CUDA file, the CU file, is the one that we're going to be heavily modifying anytime we make a GPU plugin. Essentially, all roads start from this CUDA file. And if we right click on it and go to the properties, you want to be cognizant if you're in the debug or release section, of course, because if you make changes to the debug and then build the release version, you may have different properties. But under custom build tool, we already have a bunch of stuff set up, and we're going to go to the command line here and hit edit. This is basically the command that's run when we build our plugin. It's going to take all of this code here, all these instructions, and it's going to compile our CUDA code, convert it into OpenCL code and all of the like, all of that good stuff. And as you can see, we already have our CUDA SDK base path defined here and our boost base path, which is why it's so important that we define those up front. So the thing that it's wanting us to change here is very important and it's easy to overlook. We've already gone into our procamp CUDA file, selected the properties, and we're in the custom build command line. But what we need to do now is update the version of our MSVC. This is basically going to be a tool that it uses to compile everything and get everything set up. But it's very often that this version does not match what your computer has. As you can see, it's a very specific version. So if you have a different version of Windows or VC tools, then it's going to be way different. So what we're going to do is find the line of code with this specific version. You can see we have VC install directory, tools, MSVC, and this number here. The easy way to figure out which version we have is to navigate down here to where it evaluates the whole path and just copy everything before that version number. Then we'll just put it inside of here, and you can see we have two different versions actually. So in this case, I'm just going to pick whatever one's newer, and it technically looks like this one. So I'm just going to copy this bit and paste it here. Sorry, it needs to be pasted up here. Now, that code is basically the same, which means it's probably going to work just fine. But if it wasn't, you would want to change to the other version. And once we hit OK, you also, of course, want to update this for the release version. The release version will take a separate change to apply. And if you want to test that this works, that you did everything right, hit right-click, compile on the CU file. If you get an error, something's up. You might need to change the version still. You might have missed installed or the environment variables, but you should say you should see succeeded, and that's a good sign. If you don't, just mess around with the compile settings, and you should be able to figure it out eventually. The biggest thing is just changing that version to get it to actually compile. Another thing we can do is right-click on the CL file and compile as well. And as you can see, that's going to provide an error that we're going to have to deal with as well. So this is an error that I actually recently found out and prevented me from making this tutorial several times. Inside of your CL custom build command line properties, you can see here there's a reference to Python. Now the way we call Python is highly dependent on the version of Python we have. I believe it goes version 3.8 and before you call Python, but versions after that you actually call Py. So if I change this to Py, hit OK to apply, that rhymed, hit compile, now we're going to see we have success. So once we get our CUDA and CL files compiling just like this, we are in good shape and basically ready to move on to actually looking at the meaty code and coding our GPU plugin. So let's head on over to the Mac and see what we need to do on the Mac side of things to get this to work. All right, so same thing on Mac. You can have these GPU instructions launched up here. You can see these are a bit easier to set up on Mac. First, we need to use Boost to process the GPU kernel files. We need to install Boost on our machine. We can do it through Homebrew or a direct download. Once Boost is installed, obtain the installation path. Usually it looks like this. Then we're going to open the project and do some other stuff. So the first thing I'll do is let's just do a go-to folder. We can say user slash, try and copy this here, local, and let's see if we have a seller. As you can see here is the folder that we have previously pasted. We have version 1.78, similar to our Windows system. And basically, all you want to do is, again, go to boost.org, and you'll download the file. And in this case, we don't have to do anything as fancy as, just running the build files. We're just going to take that folder and paste it in this seller folder. And then in our root, you're going to have, again, the license, the bootstrap, the index.html. And this is all going to be located in this user local seller boost folder. And again, the root just has to be this guy here. And this is just the place we're going to store it. Then we need to go ahead and open the SDK ProcAmp Xcode project file. We're not in Visual Studio Code, obviously. On a Mac, we're using Xcode. And now it says we need to go into the Preferences, Locations, Custom Paths. Settings, I guess, in the new version. And then we'll go over here to Locations. And you can see we have custom paths next to locations. And here I've predefined my boost path, but if we wanted to do it from scratch, let's go ahead and do that. We'll create a new one. We'll call it boost base path. I guess we can just, does the display name matter? Let's see if this display name matters. Boost base path, boost, and then the installation path. So we need to relaunch those settings. All caps for boost. And then for the path, again, we have it right here. I guess we need the boost path as well. So we'll go one more level in, copy that, paste it in the path, and just like that, we've installed boost. There will be sometimes a way we specifically need to add it to our build settings. So I do want to show you that as well. If I go to my project here, you can see we have these frameworks now for Metal and OpenCL. But if you ever have issues basically where that custom path doesn't work, what you can basically do is under build settings, we can find where our header search paths are, and then you can just add boost to here. And what that will do is just make sure that boost is included properly. But as you can see, that's as simple as the setup is for Mac. So let's go ahead and I'm going to hop over to my Windows again because it's a bit easier to explain and debug stuff on there. But that's the basic first setup. Now we can finally go over the code base and how to start getting started modifying the GPU code itself. Also, I had intended to say this at the beginning of the tutorial, but here's a cool example where I made this quick map maker plugin, which basically just lets you calculate different mats. And GPU wise, each of these frames takes 1/10 of a second. So we're talking up to 10 to 20 frames a second just for this simple plugin I have here. And that's just a cool effect that will be way faster than doing it with, for example, a CPU plugin. So first thing I want to do is just compile and run this on Windows just to see that it works. We already kind of fixed the CUDA and the CL setup, but I'm going to change the name of this to SDK ProcAmp tutorial and change the match name as well so that it's unique. Now, I don't know if I actually set up the debugging on this. Nope, I did not. So we'll go ahead and choose debugging, browse. And like usual, we'll select whatever version of After Effects we want to test in. And let's go ahead and compile and run. Launch the application. And the illustration of this is just going to see what does the base plugin look like. And then from there, it will make a little more sense as we dive into some of the more complicated code it contains. So we can go to Effect, Sample Plugins, and I don't think it's being installed correctly. I don't think it's being installed to the right location. Let's take a look at General Output Directory. I'm just going to manually set it to my own folder here. And Control Shift F5 to restart this and see if we can get it to load up properly. All right, select the layer, Effect, Sample Plugins, SDK Invert Proc Amp Tutorial. So as you can see, here's the invert part. It's obviously inverting our image. It's not optimized for multi-frame rendering. That's good to know. I did use the SDK from an older version of After Effects, which should be noted. But the point of it is obviously to get the GPU working. So we can check out the properties here. We can adjust the brightness, the contrast, the hue, and the saturation. And this is loading even faster than the one I just showed you. This is only 10 milliseconds. We're talking, there's 1,000 milliseconds in a second divided by 10. That's like 100 frames per second. Albeit this is like a 512 by 512 image, that's still very fast and much faster than you would get from a CPU plugin. So that's the basic effect of what this base plugin that they give us is designed to do. Now, I hope you're ready for a bit of an adventure. I hope you've got a snack. I hope you've got something to help you focus, maybe a little drink or something, because I've just gone over the setup for the first 30 minutes. Now we need to go over the giant amount of code. I'm not going to explicitly say every single thing, but I'm going to give you lots of tips and tricks about what I learned through the past months of figuring out how this works, as well as how to set things up yourself and how to go forward with learning this. So the main thing we really do want to look at for now is just the CPP file. You're going to notice a lot of differences between the header and the CPP of a normal plugin. So the first thing you'll notice in your header is you have a bunch of things like checking for CL and metal. These are just things that are automatically set up that need to stay that way. And then if we scroll down past our enumerations and predefined values, you can see we have a thing that checks it if we have metal. There's some kind of setup we need to do initially. I gotta be honest, a lot of the metal stuff is pretty advanced and not well documented, especially by Adobe. So the information on a lot of these specifics I don't know right now, but maybe in the future I will. And then we have a definition of a struct here, which is just what we're going to be using to send variables to and fro different functions, including our GPU kernel. In this case, it's an invert proc amp param, because each of these values here in our structure is going to correspond to the UI values that they're set to. That's pretty much it for the header. A lot of the stuff now is in the CPP file. We're going to just scroll down here. You can see the first thing, if we have CUDA, we're going to include important CUDA files. Now you would immediately get errors on here if you hadn't installed CUDA properly and then basically made sure your environment variable is set up. So that's an important thing to note. After that, we have just basic inclusions, a OpenCL error handler, which we'll just leave alone. And then we have a couple of kernel definitions. This part really got me at first, so listen closely. Essentially, inside of your CUDA file, we have what are called kernels. These kernels are basically functions. We have under NVCC, which is the NVIDIA CUDA core, I believe, we have invert color CUDA, which is a function. We have procamp CUDA. These then run their own individual kernels. These basically, inside of the CUDA, these CUDA functions need to be defined in our CPP. So in this case, we have a procamp CUDA defined, and we have an invert color CUDA defined. These also need to make sure all of your arguments you're sending have the correct data types and all the like that. If they are misordered in any way, it will also cause a major issue. Continuing on, we have about normal global setup. The only difference here is that we are basically adding the outflag2 underscore supports GPU render, and this is going to allow it to know if we are in After Effects. We see we have a Premiere statement else, which means we're in After Effects, we're going to add the flag to support GPU. A lot of this you don't necessarily have to worry about unless you're hard porting. If you're just taking an example project and converting your project into that, a lot of this stuff is already there and set up for you. But in this case, it's just good to know a lot of these little things. Under param setup, it's just the same as normal, where we have all of our UI definitions. Then we have some more if has metal, basically checking, hey, if this is a metal Apple Silicon computer, then do some of this stuff to check. It's just an error check. And then we have GPU data initialization for OpenCL. This is going to be to handle the CL kernels. So you basically need to keep track of your kernels. If I have a kernel to tint the image red, a kernel to tint the image blue, and a kernel to tint the image green, all separate kernel functions, we would need to have them all defined here, which would be 3 of them. And this is going to be important as well if you're using OpenCL, of course. So the kernels need to be matched up in all 3 Metal, CL, CUDA setups. Then again, we have the same thing here for Metal. In OpenCL, we're making sure we have our kernels defined here because we need to know how many kernels need to be allocated. Same thing with Metal. We need to allocate for each of the kernels we have. It needs to match 1-to-1 with the actual physical amount of kernels you're setting up. Okay, then we have a GPU device setup. Here you don't need to worry too much. A lot of this is just figured out and placed in there for you. You might be able to tweak the settings and figure out some of this stuff, but basically this is just where you set up the GPU. If we identify we have a CUDA GPU, we're going to simply add the out flag. If we identify we have an OpenCL GPU, there's a bit more stuff that needs to be done. And then, of course, if you have a Metal GPU, there's other stuff that needs to be done as well. The Metal and CL actually have a lot more setup, which is slightly annoying, especially when you're actually testing on these devices. You can see in here on the defined OpenCL section, we have our 2 kernels defined here as well. So again, if you have more kernels, you need to put these other kernels inside of here to match up appropriately and not have errors. And same, if we continue scrolling to the Metal, you can see we have our 2 kernels defined here. The formatting is different. Don't know if this is Rust, it could be, but you basically just want to copy the code formatting to make sure all of your kernels and variables match up for each of the GPU setups. All right, so after all of that, basically just modifying the number of kernels and stuff you have in your OpenCL and Metal. Just make sure you do that at the beginning because you will forget if you're just starting in CUDA. We then have a GPU device set down. This is just code that's going to tell the GPU to relax and release all the memory and stuff that is necessary. Pretty much for this, it's just an OpenCL handler saying, hey, release these kernels. And again, I gotta say this again and again. If you have another kernel, put it in there. Some of the first biggest problems I faced with GPU setups in this method is the kernels matching and the variable order and formatting matching. So now we're into some actual functions, but these are some more CPU functions, I believe. Well, this is specifically for, this appears to be Premiere formatted. So I'm not 100% if these are running on GPU, but these are basically our Premiere functions right here, which will be indicated and started by our render function, which you can see is quite simple. Render function actually is just taking in these variables from our UI and applying the values calculated directly into the destination pointer data. A little bit complicated, but we're not really here for this type of code. We are here to find the GPU code. So we have pre-render, if you're not already familiar with Smart Effects and SmartRender, check our previous video on that. But basically, this is where we grab our param data and set up the variables properly. So of course, we have our brightness, contrast, hue, saturation, setting these up into our, in this case, info pointer, which contains everything. And our info pointer is defined as an invert procamp params. So just like normal, we have a certain type of struct we define in our header file to contain our, usually our UI data and sometimes a few extra things. We're just setting that up here like normal and setting up our layer and checking that out and stuff. Now, you can see here we have SmartRender CPU, and that means there's a SmartRender GPU as well. Before we just jump into those, Between them, you can see we have another definition of a struct here. In our header file, this is where it can get kind of confusing. In our header file, we have this struct defined called invert procamp params, which contains brightness, contrast, saturation. But over here, we have invert color params. So not quite the same name, but we have a struct defined separately here in our CPP file. This is containing our source pitch, destination pitch, checking whether or not we're in a 16 bits per channel setup, and our basically image width and height. So just saying that we have this defined struct there, which is important to know because we will be using these values quite heavily inside of our CUDA functions. So we have another type struct here. This is for the procamp2 params, which I guess you could technically define this in the header file, but you can see here it says this structure mirrors that used by the metal kernel. Just leave it where it's at for now, and you can kind of learn how to modify it later. But this one, as you can see, contains the source pitch, destination pitch, width, height, and also our brightness, contrast, and hue and saturation. So those are just struct definitions. Takes a little bit of practice to get used to, especially when they're in different files and have such similar names, but try not to get them confused because if you do type in the wrong one, it can cause big issues by sending the wrong variables or sizing of variables to CUDA. Okay, Smart GPU, we're about to get to. We actually first are going to look at our effect main. You can see we have a few different things that are different. We have a GPU device setup and set down. We kind of briefly went over those. That's just initializing the GPU to get ready to process and then telling it to release any memory and issues once it's done being used. We have our normal render and we have a smart render. We actually have two smart renders. One of them detects if we have a normal smart render, the other detects if we have a smart render underscore GPU, which we're basically just running the same smart render function with a different bool argument here saying true or false. So if we go to our actual smart render function, you can see that we have this bool is GPU. Are we going to run a GPU function? So all we're basically doing is using an if statement. Are we running GPU? Cool. Do smart render GPU. Are we running anything else? Okay, then we need to use CPU. And there are also cases if you do run GPU and have issues, sometimes After Effects will revert to the CPU just because it knows that that's going to work as opposed to a broken GPU kernel. And again, I do want to remind you, I have documented all of this in the GitHub repository link down below with a bit more explanation than I may be giving now. But I'm pretty much going over everything that's described here, just to go over the basics and stuff that you may misinterpret or get confused by. But now we can finally look at SmartRenderGPU, which technically isn't even the end of the line. This is just to prepare things for the actual GPU processing. So inside of here, we have all of our normal in data, out data, pixel formatting, input world, output world, and our info p, which is our basically struct to contain all of our param data. So this is where we're going to be doing sort of three splits. We're going to have a separate section or sort of a general section which handles all the GPU world setup or the layers setup. And then we have three splits into OpenCL, CUDA, and Metal, which all have to be accommodated and matching each other. So as you can see here, we just have some setup to create a buffer. A buffer is basically an effect world. And we're also going to use special functions like create GPU world to fill these buffers, in this case with our input world. Then we can do things like have a source world, a destination world, and an intermediate world. So if you wanted to, you could just have a source world, write that to an output. Or if you have multiple intermediary functions, you can use an intermediate world, which is using our intermediate buffer. The in world or the source world is using our input world. The destination world is using our output world. And then our intermediate is just sort of empty for now, but we can fill it up if we want to. Then we're going to have some definitions for our param setup. We're going to set up our width and height. All of this is to calculate the pitch, which we discussed earlier, again, is an important multiplier so that we can properly parse and look at our image. Then we're going to set up, of course, our brightness, contrast, hue, and saturation based on our struct here, which contains the information directly from our UI parameters. And then we have 3 if statements to finish up the CPP file. All right, the first thing we do is we check, is this OpenCL? Is this CUDA? Or is this Metal? Firstly, if it's OpenCL, probably the second most difficult setup here. First thing we do is we set up some worlds. Again, these source memory, intermediate memory, and destination memory are just sort of placeholders. We can use them mostly in our OpenCL here, but we're going to convert them to an OpenCL world basically. So we're going to convert source mem to CL source mem. We're going to convert intermediate mem to CL intermediate mem, and the same for destination. Just a slight conversion to this CL mem type to make sure that they work in OpenCL. Then what we're going to do is set the arguments for each of our kernels. Again, remember we have 2 kernels. We have our procamp kernel and our invert color kernel. The invert color simply applies the invert effect, and the procamp applies the brightness, contrast, hue, and saturation. So we're going to basically have 2 kernels that we need to initialize. And if you can guess, the separator is right here. You can see we have set kernel arg, set kernel arg, set kernel arg. This is super important. The first argument needs to be your source world. The second argument needs to be your destination world. Then it needs to basically be all of your other arguments that you've defined. So we have our pitch, destination pitch. Is it a 16 bits per channel? What's the width? What's the height? Then we're going to set up a basic thread block, which by default 1616 is fine. You can mess around with this, but generally it doesn't make too big of a difference. And then we're going to apply this as a grid, and then to initialize our kernel with these arguments we set up. Again, the arguments have to be in the same exact order as they're defined in your actual kernel. In this case, you can see the invert is source, destination, pitch, 16, width, height. And same here, it's source, destination, pitch, 16, width, height. It has to match. Just because in this particular case, if I was to switch this, then our height would become our width and vice versa. It's also important that all your data types are accurate, so make sure you have like a CL mem and an int for these particular ones, because if your size of is incorrect, if I use a float, for example, it's not going to work. All right, and now to basically initialize the kernel, now that we've set up all of the variables, we're just going to call CL NQ ND range kernel. This is going to basically, we're going to provide it with our invert kernel, or if you wanted to, you could provide it with the procamp kernel, and that's going to run it based on these variables or arguments we set right here. Now, after that, we're going to do the same thing for our other kernel, our procamp kernel. In this case, let's take a look at the variable order. For procamp, we have source, destination, pitch, 16, width, height, just like the previous, plus brightness, contrast, hue, saturation. In our CPP file, we see the same thing. We have a source, destination, pitch, 16, width, height, brightness, contrast, hue, saturation. One thing that beginners in this GPU setup can get confused is that by default, this is going from source to intermediate memory, and then intermediate to destination memory. So if I was just to remove this second kernel, this isn't going to produce anything, because we're just going to an intermediate world, not our output destination world. We would need to switch this to be our destination mem instead, if we just use this single one. But because we're doing 2, we have an intermediate one, we're going to reuse it by using the intermediate memory, then to the destination. The destination is always the final place to go to make sure that it appears on your screen. This can be a big issue I've had. Now that's pretty much it for OpenCL. As a quick recap, you basically just need to define your variables up here, your worlds, and then set the arguments one by one in the proper order, in the proper variable format, and then initialize the kernel and run the active kernel using range kernel. All right, now we can move on to the CUDA part, which is, in my opinion, the easiest. If we have CUDA, you can see it's just these couple lines of code here. We're going to run our invert color CUDA function, which, yes, I defined as being here, and I was discussing them for the OpenCL, which is kind of a faux pas. I haven't really discussed the CUDA file too much, but we're going to get to that in just a sec, which will make more sense, why we have all these functions and kernels and methods. So same thing, we're going to run an invert kernel, then a procamp kernel. Same thing, we're going to have the same, we don't have to queue up our arguments in this case, we can just pass them like normal. And we can even go to the definition of this, which we have here, just to see all of them. In this case, we need our source, destination, pitch, 16, width, height. And these are all based on our invert proc amps struct we set up and got all of that stuff from info-p. I know it's a lot of explanation, but I just want to be explicit and fully detailed because I've been doing this for a while. Then we're just going to make sure the CUDA doesn't present an error, which is fine. If it does, we're going to tell the error we have an internal struct damaged. Then again, we have our source to our intermediate. If I was just to delete this, it's not going to work because this isn't our destination memory. Our destination memory is being set here on our second kernel where we have source destination based on our intermediate to destination. Basically, the input world is our intermediate and our destination world is our destination. And then all of our arguments passed. A lot easier than I'd say the CUDA set or than the OpenCL setup, but now we have also the Metal setup, which is a lot of fun. So with Metal, you just kind of have to do your best. Unless you're an experienced Metal programmer, you just kind of have to copy and hope it works. It's not too hard, but it does take some practice, especially when it's grayed out and you can't see variables as well. So there's a whole bunch of stuff I don't have to explain because it's just kind of required for setup. So we're basically going to set up a device and all of our parameters for each of these buffers. So we have our proc amp params. We got to get the length and size of it so it allocates the right amount of memory for our specific Metal GPU. And then we're going to do the same thing for the invert proc amp. Then to launch the command, we have a queue, a command buffer, and a compute encoder. These are basically just tools that allow us to do the computing and setup. Then we have our buffers set up. These are the metal worlds, basically. We have our input source world, our intermediate metal world, and our destination metal world, which again are one-to-one with the CL and CUDA, where the source is going to be our input world, the intermediate is going to be empty until we fill it with something, and the destination will always result in our final image. And you can see we're using our source mem, immem, and destination mem variables that we used both in OpenCL and CUDA. We're just converting them to an ID metal buffer type. All right, so the same way we cast these to an OpenCL buffer, we're casting them to a metal buffer. Then we're going to set up threads for the invert proc amp, or for the invert kernel, and threads for the proc amp kernel, which are based on basically our pipeline. Again, these are kernels we set up previously. Up here, we defined all of our kernels, which are important, and then as well the size of our image based on the width. Now, finally, how do we execute in Metal? How do we execute these methods and functions? We use our compute encoder. The first thing we do is set the pipeline state using our kernel. Then we set the buffer. The first buffer is our source, so we're going to use our source metal buffer. The second buffer, or second argument really, is our output, which we're going to first use as our intermediate. So we have the kernel that we're setting. We're saying, hey, we're going to set up the invert kernel. Then we're going to set up the source, the destination, and instead of doing the arguments one by one, we just provide the whole entire structure, in this case, invert param buffer. All right, and then we just have the dispatch thread groups, which is telling it what kind of threading values to use. And we also have this error check afterwards. If there's no error, we're going to also go forward and do the proc amp kernel, where we say, hey, currently the pipeline state is going to be set to the proc amp kernel. This is going to be our source world. This is going to be our destination world. Here are our variables from our struct, the threads, and the slightly different thing about Metal is that it looks like on the very last kernel you run, you have to put this compute encoder and encoding and command buffer commit. If we were just to have the single invert proc amp, we could just then put it here, and I believe these are important to actually go through and finish the process. Are you still there? I don't imagine many are, but if you are, congratulations. You've gone over most of the setup and things like that. Finally, we're going to take a look at the CUDA file, which is the last sort of fun stuff that we get to finally do. Inside the CUDA file, we have two sections. We have the section which we define all of our device-specific kernels. These are going to be denoted by GF kernel functions. So we have a GF kernel function for our proc amp kernel and a GF kernel function for our invert process. At the bottom, this section is specifically for CUDA. I don't know why it's separated like this, but this section here is for CUDA specifically, where when in our C++ file, we have our has CUDA, these are the functions we're running. We have our invert color CUDA function and our procamp CUDA function. These are both defined here at the bottom of our CUDA file, which basically just has our input arguments. It has the block size and grid dimensions we're going to use, which are important for setting up basically how much GPU to allocate. So you can mess around with these values and try like 32, 32, 1, things like that. And then finally, if you're familiar at all with CUDA, the way we call a CUDA kernel is by calling the name of the function, using these three carets, our block and grid dimension size, our variables, and then at the very end, we're going to do a CUDA device synchronize to basically catch everything up and send it back to After Effects to display. So we have those defined there for CUDA. So what are these up here for? Well, basically, these are sort of universal kernels, I would call it. And these universal kernels are going to be interpreted automatically into OpenCL, CUDA, and Metal. And that's why everything here is located in this CUDA file. Our CL file just references the CUDA file because it's going to compile the code from here into the format for us automatically. That's sort of the beauty of this GPU setup, is that we just code it once and then automatically interprets for the most part to the other types of GPU setups. The only difference is variable setup, kernel setup gets a little nitpicky, but other than that, everything gets reinterpreted automatically. So a quick word on the way these are formatted. Basically, we have a gf kernel function, the name of it, this is the name of our function. Then the order of the variables is always very specific. The first argument is the input world, then it's the output world. You can see there's no comma between them as you might think there should be. So the input world and output world are sort of two values right next to each other as the first argument. Then for the next set, we also don't add commas for all of our arguments that we've set up. So our pitch, 16, width, height, brightness, contrast, hue, saturation, all of those go right after each other, making sure you're casting to the proper value here. Floats do work really well with GPUs, and then a comma at the end of all your arguments. And lastly, we have this uint2 in xy, kernel xy. This is basically to denote and give us access to the current xy pixel value that we're looking at and processing. So let's just do it, okay? Here's what I'm going to do. I'm going to go into my C++ file, and because we're using CUDA, I'm just going to do invert. So I'm going to get rid of this procamp, and that should be fine just to do that. This means that the brightness, contrast, hue, and saturation values aren't going to do anything. We're just going to invert the image and look at this invert color kernel. So this is our procamp kernel. But here's our invert color where we just have the basics. We don't have any external arguments to mess with. But the actual code here, what are we doing? We're looking at the in xy point, grabbing the x, and we're making sure it's within the bounds. So we're saying, is our x value less than the width, and is our y value less than the height? If so, good. We want to process this pixel. How do we read a pixel? Well, pixel in CUDA, or in this format essentially, is a float 4 value. This means that we have 4 values within here. We have an x, y, and a z, and a w. Now, we also need to take note of the formatting when we have these 4 values. This is actually to say A, G, B, R, I believe is the order. So we have our W, X, Y, Z. Our pixel.x is our B value. Our pixel.y is our G value. Our pixel.z is our red value. And our pixel.w is the alpha value. It's A, B, G, R, W, X, Y, Z. Hopefully that makes sense. I had to write it down for a bit at first. So this float 4 pixel just basically means 4 float values, X, Y, or W, X, Y, Z. The way we read pixels is quite simple. We say read float. We want to read a float 4, a pixel basically. We're going to give it a world. This could be our input in source or out source. And then we're going to give it a pixel to check. I mentioned this briefly before regarding the pitch. You can see we take our Y value, multiply it by the pitch. Then we add our X. So we have a grid here from basically the origin at the top left getting greater as we go to the bottom right. We're going to take our y value and then multiply it by the source pitch. This will basically give us the equivalent pixel on the grid for this y value. And then finally, to finish it, we add an x to get the proper column that we should be in. And hopefully that visual is enough to understand how that works. We're basically just using basic math to multiply the y value by the width, add an x to get the actual pixel value. Then we have this thing which checks basically, is this a 16-bit or bits per channel layer? 2 exclamation marks in 16F. Just leave it there, let it do its thing. It'll automatically parse the values appropriately for the most part. Then you have access to some other functions like fmax, fmin, and the like. In this case, what I want to do is just manually define these. So I'm going to say our pixel.x is equal to 1.0. Yes, we just read the pixel here and got its actual value. This is basically how we sample a pixel, right? We're sampling a pixel at this location, but I'm going to change the values on purpose. So our b is going to be 1, and everything else besides the alpha will be 0. And we're going to just put these f's afterward to indicate these are float numbers, and then for the alpha, 1.0. So this will say fully opaque blue pixels for all of our pixels. And then finally, to write this pixel back to the output layer, we're going to give it the pixel that we're writing, in this case our float4, just called pixel. We're writing float4 is a pixel. We're going to write it to the out destination, the out world. And again, we're going to tell it this is sort of the index that we're writing it to, and then our check for 16 bits per channel. So if I recompile this and run it, we're going to get an error. Let's go ahead and see. Expected a colon. Semicolon. Yeah. Just remove that and rerun it. And again, we're just running the invert function now, which we've modified to make every single pixel hopefully pure blue. So we'll go ahead and apply our sample tutorial. And as you can see, some of these frames were cached. So let's go ahead and purge our memory and cache, which can happen quite quickly sometimes. And you can see we are upside down. And again, remember I mentioned, if you're writing to the intermediate world, you're not going to get a right output image. And that's exactly what I just did. You can see I removed this code here and didn't follow my own instructions. We're going from source to intermediate. This needs to be source to destination. Because again, our destination is a pointer linked directly to the output image that appears in After Effects. So again, we'll load up our test here. And now you can see we get a pure blue image. And look how fast that blue image is, 9 milliseconds, so fast. Again, we set it up so these values aren't currently doing anything, but now we basically have the ability to start modifying our CUDA kernel and doing some really cool stuff. I'm not going to go into super depth on what you can do, because a lot of it is the creativity you bring, but just remember we have our read float4. This allows us to sample pixels. I can sample pixels anywhere on the image. I can sample them to offset them. I can sample them to change their values. And then we have a write function. It's basically read float4 and write float4 that are your best friends. We can sample pixels and write pixels to output worlds. And then of course you can do manipulations in mathematics with anything. So if I wanted to maybe just do a basic color tint or something, I'm going to set pixel x to be itself divided by 3. We'll do pixel.y divided by 2. And then we'll just do pixel.z. And this should just modify the sort of base pixel values and divide them by themselves to make them more muted, and in this case, stronger on the red channel. So this is just a quick mathematical way we can make more than just a solid color modification to our pixels. Go ahead and apply our effect. As you can see, it's a bit of a like reddish tint right now because we're taking our blue and green channels and dividing them by 2 and 3 to make them much smaller, and our red channel is basically remaining the same. And as you can see, it's a nice, quickly loading look. And just again, a quick tip, if you do see artifacts like this is from a previous build. One thing with GPUs loading so many frames and caching them is we got to clear our memory a bit more often than usual. And one last thing to mention is you can also check out all of the other stuff that you can do inside of this kernel function. You can say right click on read float4, peak definition. It's going to take you into your kernel memory header file, and this contains all of the different methods and stuff we have access to, whether it involves floats, float 2s, float 3s, float 4s, and basically will give you a little bit more insight into all the various things you can access inside of the new GPU setup for After Effects. If you guys enjoyed this long tutorial, probably the longest, most detailed one I've ever created, hit the thumbs up button down below, subscribe, and all the like. Again, the code for this will be, the code and the guide will be in the description down below. Make sure you follow us there on Instagram as well. Subscribe and become a member, and enjoy making GPU plugins. This can be a very fun and also a daunting thing to do, so if you have any questions, leave them down below. But we will see you guys next time.